Hello and welcome back. In section 6.2, we'll be talking about integrals with a square root of a squared plus x squared, or this technique will apply also with a squared plus x squared in the denominator. All right, so our goal is to evaluate integrals which contain the square root of a squared plus x squared using a different inverse trig substitution. Right, so we'll apply a similar procedure to integrals that contain the square root of a squared plus x squared, really close to what we did in the last section, just not using sign. Note that this method also works with integrals of 1 over a squared plus x squared. That's like a bonus, right? Our goal is really to integrate these, but it also applies to these, which is nice. All right, so let's start the same way we did last video, sorry. Example 6.2.1, evaluate the integral from 0 to 2 of 1 over square root of x squared plus 4 dx. So I'm going to start by trying to build a triangle. I want a triangle. I want one that has square root of x squared plus 4 as one of its sides. Now, because I have two positive number, I'm forced to put that as the hypotenuse here, and then I have x and 2 to put. I'm going to place them this way just to simplify things, but the other way would work as well. It's just that you'd have to work with cotan, which we try to avoid. All right, so here if I read from the triangle what tan is opposite over adjacent, so it's x on 2. So x is 2 tan theta. So instead of using sine, when you have pluses like that, you'd be using tan. And then you differentiate tan, you get secant squared theta d theta. All right, so I'm using these two to get what x is. I'm using opposite over adjacent, x on 2, and I get this. Now, if I want the square root, I'm going to use these two. So you could use cosine or secant. I'm going to use secant just because I know what's going to happen. Secant is hypotenuse over adjacent. That's going to get square root of x squared plus 4 divided by 2. And so my square root, the one that scared me first inside my integral, is going to be 2 secant theta. All right, so notice that they're not actually the same. In the preceding one, they were the same, but that's just random. Here, the derivative is secant squared. This one is secant theta. So don't think they're always going to be the same. All right, let me rewrite this. I have 1 above, that stays 1. I have my square root, so I'm going to put that in. And then I have dx. Never forget dx. So dx gets put in as well. I'm going to simplify. The 2's cancel. I'm left with just 1 secant theta d theta. All right. I have bounds, so I need to deal with the bounds. Here, theta is, if I isolate here, that's going to be easier. I'm going to put the tan on the other side. It's going to become arctan. That's the inverse function of tan. So arctan of x on 2. And so that's what I'll apply here. Arctan of the old bound divided by 2, arctan of the old bound divided by 2. So arctan of 0 divided by 2, arctan of 2. So arctan of 0 is 0. Arctan of 1, that's one that you should know. What angle gives you a slope of 1? 45 degrees with pi on 4. All right, then I get ln. That's one of the integrals that we learned. What is it? Ln of absolute value of secant theta plus tan theta. And then I plug in 0 and pi on 4. So I get ln of secant of pi on 4 plus tan of pi on 4. Let me put it here so I have enough room to write everything. And then minus log of secant of 0 plus tan of 0. So that's ln pi on 4 would be root 2 plus 1. And then secant of 0 is 1, log of 1 is 0. That's it. Let me just write it here. Secant of pi on 4 is 1 over cosine of pi on 4, which is 1 over root 2. So it's just root 2. All right, so here's the method to integrate these types of functions. So you use the substitution x equals a tan theta. Tan theta is x on a. That tells you how to build your triangle. X on a, opposite over adjacent. The remaining side is going to be x squared plus a squared. That matches the square root that we have right here. That's why we do it. Then to get the dx, you just differentiate tan and you get secant squared. The square root here is a secant theta. And then if you want to look at what theta is, you send tan to the other side, you get arctan of x on a.